In this video we use our knowledge from the last part and create a 4-bit adder. In the last part we set up these equations. To create the circuit for the 4-bit adder, we do the same as last time and translate the equation into corresponding functions of the half and full adder. Now let's build this circuit and see how it works. Now let's take a closer look at this circuit. In particular, we look at the initial values and the result. Of course, as you would expect, 0 plus 0 equals 0. Two plus 3 and 6 plus 7 also give the correct result. That's fine as long as you don't get past 15. For example, 9 plus 8 results in 1. Only when you include the additional bit in the calculation will you get the correct result of 17. This additional bit is commonly referred to as carry. It usually serves as an indication that the result has gone out of range. But you can also use it in other ways. To do this, we first define two 8-bit numbers and add them together. We now summarize everything and replace the known expressions with our adder. We notice that there are 2 bits left here again. The bit C0 should actually be added to Z1. Now we expand our circuit based on these considerations. Let's first look at our example from before. Now 9 plus 8 is actually 17, as expected. Here, too, there is 1 bit left at the end, now the 8th. As you can easily verify, this concept can theoretically be expanded infinitely. Now let's create our new component. We use this command line. We do everything we have done so far. For the calculate method, we translate our circuit into code. I use 4 full adders here. The Intel 4004 always uses carry. For the fast method, I calculate the sum mathematically. And don't forget to adjust the main scripts. Now we rebuild our circuit and use our new component. So far we have always tried out all the options for testing. But this time there are 512 possibilities, so you need a little help. We start Blender from the command line. We take our circuit and first rename switches and lamps. Although this is not necessary, it makes it easier for us to write the script. We switch to scripting. We create a new script and import BPY. We look for the required objects from the scene. Now let's define a few variables. Next, let's create the method that will do the work for us. We access the global variables. In mode 0 we set the values of the inputs. In mode 1 we check the results. Here we count up the input values in each step. This allows us to systematically go through all the options. When we have gone through the last variant, we write a corresponding output. We stop the script at this point. After we have determined the next variant, we pass the values to the objects. We update the objects for purely visual reasons. And change the mode. In mode 1, we first calculate the correct result mathematically. Then we test it and, if there is an error, we issue a corresponding message. Here too we change. After each exit of this method, the circuit script will perform the calculations. Here we automate the script. Now we first run the script, which now waits in the background for a new frame. We start the circuit and follow the action a little. At the end we get the message that there were no errors. This means we can assume that our component is working correctly. In the next video we'll look at subtraction and build a subtractor.